All right, so it is the next day. So it's time to not be listening to Spotify, but time to go ahead and do those follow-up questions. So I basically have four: hybridization about carbon and phosphorus, induced versus instantaneous dipoles, London dispersion forces, and some exam questions. So the first one of these is to talk about the hybridization for carbon and phosphorus. So one of the things about both of these is whenever we're talking about hybridization, keep in mind that hybridization is going to be based on the number of electron domains. So whenever we talk about hybridization, hybridization is always going to be based on electron domains. So because it's based on electron domains, that means it really depends on what's going on. And what I mean by this is when we think about carbon, we are thinking about the fact that carbon can do a lot of different things. So carbon could have two electron domains. So this could be triple bonded to another carbon and single bonded to a hydrogen, for example. Carbon could also be double bonded, in which case I'm just going to use a bunch of carbons and hydrogens to make my life easier. So this would be sp hybridized. This would be sp2 hybridized. And of course, to finish this out, carbon could have 4 electron domains. And then we are sp3 hybridized. So whenever you're talking about the hybridization of anything, keep in mind that we still care about electron domains. So while there are some differences, mostly in the fact that in all of these, carbon doesn't have any lone pairs. Other than that, everything's going to be very similar. That being said, if we did want to use, usually when we talk about carbon, sp3 is usually the hybridization that we're discussing. So when we start to take a look at carbon, we always start from our valence bond theory. So thinking about it on the periodic table, there we go. Here's carbon. So this is going to have for my valence electrons two 2s electrons and two 2p electrons. So when we take a look at carbon initially, from what it has in its ground state, it looks like this. And the thing is, if we were only doing valence bond theory without any hybridization, valence bond theory alone would predict 2 bonds. Because we only have 2 electrons in alone in orbitals ready to bond, which is why we then turn to hybridization. So hybridization is what's going to allow us to change these around, so we can then go ahead and deal with the fact that what we'd really like in this case is to deal with those sp3 electrons, take my 4 electrons, move them around. Now, just since I did bring up, so that's how we get the hybridization for sp3. We basically take one of these electrons, move it over here, and then mix them all together. Now, if we were trying to get any of the other shapes, so that was for the sp3. If we were aiming for sp2, realize that we would still begin with the same 4 electrons, but then what we would still elevate the 1, so we'd still move, whoopsies, over there. So we would still wind up with the excitation of 1 of those electrons. But then if we're only aiming for sp2, what we're going to do is we're just going to take some of those electrons, not all of those electrons, and only hybridize the orbitals that we need. So this then becomes sp2 hybridized. And then we actually still have one of those unhybridized p orbitals left over. Unhybridized p. So when we're thinking about a double bond and we need an sp2 hybridization for the carbon, we can absolutely still do that. And this unhybridized p orbital is then what's going to allow us to form the pi bond. So hybridization does go very well into sigma and pi bonds. So even though carbon we often talk about carbon as being sp3 hybridized because that works very well for us. We can do both sp and sp2 hybridized, and then you just have different numbers of unhybridized p orbitals. Since I said that, let's go ahead and take a look at what I meant by that. So again, if I'm doing now sp hybridized, so I'm basically working my way backwards. And I only want 2 of these, starting from the fact that we know we're going to wind up elevating. We'll just start from the beginning. So we again start here with carbon. We excite one of my electrons. So then I wind up with 2s and 2p, and those should be separate orbitals. So just drawing them a little bit sloppily. There we go. And then from here, if sp is the only thing I want, then I'm just going to combine these 2 together. And then I would have 2 sp orbitals. And then I would also have unhybridized p orbitals. So now these would be ready for a pi bond. And again, each one of these individually could overlap to form a pi bond. Triple bonds have 2 pi bonds. I have 2 unhybridized p orbitals here. So again, so carbon can do lots of different things with its hybridization. The other atom that was asked for was phosphorus. Since he asked about phosphorus, I'm going to assume that we're looking at the textbook example. The textbook example talks specifically about PCl5. It's supposed to be chlorine. 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 Lovely. So for this, we again are starting from the same place as far as the periodic table. So we are starting from, here is phosphorus, 5 valence electrons. So we're starting in the 3rd period. So since we're starting in the 3rd period, that is 3s and 2 electrons there, and 3p and 3 electrons there. It's 5 valence electrons. And then we're just going to go ahead and put the 3d in there because they exist. Phosphorus is in the 3rd period and below, so it can have an expand octet. It actually is utilizing those d orbitals in order to do this. So we're just going to reflect that. We're playing the same game. We're going to excite one of these electrons so that phosphorus can go ahead and actually have the correct number of electrons ready to bond. Three S, 3P, 3D. And then all we're going to do is mix these together. So then I get 1, 2, 3, 4, 5 sp3d electrons. And technically I have some other d electron 3d that I left alone, but there's also no electrons in them, so they become a little less interesting. So yeah, so again we're using that combination of valence bond theory stating that in order to form a bond, I need to have an electron alone in an orbital in order to form a bond. So before we did any finagling, any changes, phosphorus could in fact have 3 bonds. So phosphorus can have 3 bonds by the valence bond theory, but we know it has 5, and so we are going to use hybrid orbitals. In fact, we'd use hybrid orbitals no matter what, because valence bond theory will actually still give us the incorrect bond angles. So we are all about hybridization. Valence bond theory just uses atomic orbitals, which is why it's got some problems. Okay, so hopefully that answered that question. Induced versus instantaneous dipole. This is one where your textbook has pictures of these, but the hard thing is that this is something that is more in motion. So it's a little bit more difficult to think about what you're doing looking back at static pictures. So I always think about these for nonpolar molecules, even though these do also exist for polar molecules. For the pictures I'm going to draw, these are going to be especially for nonpolar molecules. So a nonpolar molecule, We usually think about these as having pretend that's nice and even electron distribution, where everything is all laid out in the same way. There's even electron density everywhere. But the thing is electrons aren't static things. Electrons move. Electrons are not always in the same place all the time. So you can imagine and picture a thing where just at some random time, for no real reason other than statistically it's likely to happen, there's just suddenly more of that electron density on one side than the other. So it's a random change that's not caused by anything, and it just happens. It's spontaneous. It's you could also think about this as being instantaneous. So this is instantaneous. There we go. So this is an instantaneous dipole, where just at some point the electrons so happen to be more on one side than the other. Because of that, you wind up with a partial negative and a partial positive end to the molecule. So instantaneous also means like temporary. It happens in an instant. It's very quick. So this is just a thing that happens. It doesn't necessarily stick around, especially when it's nonpolar. But you just wind up with more electron density on one side of your molecule than the other, just because, randomly. No real reason. It just happens. That's an instantaneous dipole. When we go to talk about an induced dipole, so because I know a number of y'all are oftentimes headed for the health field, the word induced, when you think about the word induced, they'll talk about people giving birth being inducing labor. So inducing usually means like to affect, to start, where something is being purposely changed or something is being affected by something else. So it's not random. It's got an actual cause. Something is happening here. So for induced, we're still thinking about that a molecule that's all nice and even, but now, dun dun dun, it's going to wind up being next to maybe even this spontaneous, instantaneous dipole. And because it gets close to this other thing that has a dipole, so this is the one we're observing, but because it gets close to this other one that already has a partial negative and a partial positive, this, what was just a nonpolar molecule just hanging out, is now going to be, this electron cloud is now going to be attracted to this positive end. Or if I had the reverse, I could have another one being repelled by the negative end. That's not a very good pick. Anyway, it's fine. So either I could think about one of the electron clouds being attracted to a positive end. I could think about it being repelled by the negative end of something else. So then what's going to happen is, again, in kind of like a time-lapse way, here's my troublemaker from the original that I had, but now my other nonpolar one is going to basically react to it. And the nonpolar one I drew on the other side will also react to it. So basically, where before I had two nonpolar ones with no partial charges, now suddenly I have a whole bunch that are expressing a dipole. We're going to pretend that these are nonpolar, so these are going to be things where the dipole is not constant. But I'm going to have an induced dipole where my blue ones are. So the ones on the end are an induced dipole because they got close to something that already had a dipole moment. So this is an effect from because they were affected by the middle one. Which has a dipole. even if it's an instantaneous dipole. So essentially, an induced dipole just means that the molecule bumped into another molecule, and when it bumped into the other molecule that already had a dipole, it then also was induced to have one as well. So molecules can bump into other molecules when nothing happens. That happens too. But in this case, since we're talking about an induced dipole, we're assuming that it bumped into something that did have a dipole moment, even if it's just an instantaneous dipole, and that therefore induces dipoles in the other ones. So that is the difference between instantaneous and an induced dipole. Instantaneous is going to happen on its own, essentially, randomly, no reason. Induced dipole, you're assuming it's bumping into something else that's causing that. Next up was actually talk about dispersion forces. So the thing is that we just described that instantaneous and induced dipole is what typically causes dispersion forces. So when we talk about dispersion forces, it's caused from instantaneous dipoles and induced dipoles. So that's where they come from. So whenever we talk about dispersion forces, we often talk about them in the context of nonpolar molecules, and that's because this is the only thing that holds nonpolar molecules together. So these are the only attractions for nonpolar molecules. But these attractions do also occur in other molecules that have dipole moments all the time. So because these things are attractions that happen because of electron clouds, we do typically just say that all molecules have these. Even if it's a very small part of the attraction, because really at the end of the day, these small effects, one, can add up to be larger effects, depending on how many of them you have, which is why you got nonpolar substances that do in fact come all together. We do go ahead and say that everything has these. So basically, as long as you've got an electron cloud, you can have those small effects that do in fact wind up with those small partial charges that still allow things to be attracted to each other. So nonpolar things have dispersion forces, but so do so do things that always have a dipole moment or always have hydrogen bonding. Just everything has dispersion forces. So I know since those questions went by really quickly, I don't remember anybody asking me for examples of dispersion forces or London dispersion forces. So the thing is that we can do things like rank them. So when you are thinking about London dispersion forces, if you are dealing with nonpolar molecules, there's three main ways to rank these. One is by size of atoms. One of these is by the number of atoms. And the last one is with shape of molecule. So just be aware that there are ways to do that. So you might either go back to the notes and check out the ways to discuss how to rank things like that. I'm being a little bit vague because I don't want this follow-up video to be too long, and I'm already getting close to 20 minutes, and I've got an awful lot of the fall 22 exam to do, which I think actually has one of these in there. So I'm going to go ahead and move forward into doing the fall 22 example questions that folks were asking for. So I cheated a little bit and 1, 2, 3, 4, 5, 6, 7, 8. No, I gotta go get one more. There we go. This is where I'm starting. No, I'm not. Date, what? Should be from Oh, that is definitely not what I wanted. Why? Oh, silly me. I'm in Dropbox. It's like, why is the year wrong? Because I'm in Dropbox. I'm not in the right thing. There we go. There's all my screenshots. Like, why? Why is this doing weird things? Oh, well, look, it's still more chemistry. Shocker that I pull something random out of an old file and I wind up looking at old notes from chemistry from some other previous year gone by. Not a surprise. Might have been from this year. Who knows? Okay. So downloads. There we go. So I'm going to do my best to just go in order. I am grabbing things off of the key so that I don't have to flip back and forth. The element phosphorus naturally occurs as P4. It reacts readily with magnesium according to the following equation. What mass is required to completely react with 73.4 grams of magnesium? So whenever we're looking at questions like this, some wording to pay attention to, or some things to pay attention to. So one, there are already coefficients here. So since there's already coefficients in our chemical reaction, I'm going to trust them. So I'm going to trust the coefficients because they are already there. So I'm going to assume that this reaction has already been balanced for me. I am not going to double check it. I have coefficients. Life is good. From here, the other wording that I want to pay attention to is this is asking me about one of the reactants. So what mass? So I am going to be in grams. To completely react with a certain amount of the other reactant. So what's happening here is when it says completely react, it just wants the exact perfect ratio. So you'll notice that nothing particularly is in excess, but also nothing's supposed to be limiting. This is supposed to be the exact perfect ratios. It doesn't actually ask about the product at all, so I'll have to worry about that. All I'm going to worry about is I'm going to worry about my two reactants together. So we're going to start with, so we want to end up with the mass of P4, but we are starting with grams of magnesium. So the other thing to note is they actually gave me the molar mass here in parentheses. We'll come back to that idea. But a lot of times, because we know that it takes time to get molar masses off of the periodic table, we will actually often give those to you to speed you guys up a little bit. So another thing you don't have to think about or worry about or recalculate, we've got it for you. For instance, this is just magnesium. We didn't give you guys magnesium to the periodic table. I scribbled all over everything. Magnesium, 24.31. So 24.31 grams of magnesium in 1 mole of magnesium. But the question says I don't want magnesium. I would like phosphorus. So now I'm going to use my balanced chemical reaction. So whatever I have up here, I need down here. So I have mole of magnesium here up there, so therefore I need mole of magnesium down here. I'm going to look at my balanced chemical reaction. I have 6, whatever's in front here, and I'm going to go to phosphorus in 1 mole of phosphorus. And then I can go, because it wants grams, it wants mass. So because it wants mass, I can also say that in 1 mole of phosphorus, I have 123.88 grams. So I do usually do my railroad tracks all in one go because now I don't have to stop. I don't have to slow down. I can just go ahead and do all of my math at once because if you'll notice, I have grams of magnesium and grams of magnesium, so those cancel. I have moles of magnesium and moles of magnesium, those cancel. I also have moles of phosphorus and moles of phosphorus, those cancel. And I should have set up here that I have grams of phosphorus because that's what I have from the molar mass. That is in fact grams of my P4. So Now we can do this. 73.4 divided by 24.31 divided by 6 times 123.88. So this then gives us 62.34 grams of P4, and look at that. Boom, no problem. Lovely. So one done. Next up should be, just gonna grab it off here. So when I was looking at these, it looked like it was all the math stuff, and I've done very little of the math stuff in my class, so I think I was doing a lot of math, which on one hand is unfortunate. So if you have not gotten to try these out, I highly recommend you stop the video so you can try these out on your own, because I'm going to wind up doing almost all the math that's on the Fall 22 exam. When carbon disulfide with this molar mass burns in the presence of oxygen and there's a molar mass, sulfur dioxide and carbon dioxide are produced according to the following equation. Again, I actually have coefficients here. So I'm going to trust the coefficients. What is the percent yield of SO2 if the burning of 25 grams of, what was that, copper disulfide produces 40.5 grams of sulfur dioxide? So the one thing that this doesn't say, which actually I'm not super surprised, so we are given 25 grams of copper disulfide, which is right here. Let me also just underline that so it matches. It makes me feel better. So we have that, and then we are going, we want to know about the sulfur dioxide. So we want to know about sulfur dioxide. So, and you'll notice that all these are in percentages. So when we talk about percent yield is actual divided by the theoretical times 100%. So what they did is, this is the actual. So that's the number that they gave us. They gave us the actual number because you were not going to go in a lab during an exam and do this experiment to get the actual yourself. So we had to give you the actual. But the theoretical wasn't given. So we'd figure out what that is. The other thing, the only thing I'm surprised that they didn't give, but I get it, is they didn't tell you that it was an excess of oxygen. But honestly, because you only have information about one reactant, you kind of have to assume that the other reactant is in excess, because you don't have any other information about this to figure anything else out. So you kind of have to assume that the oxygen is in fact in excess, because otherwise this problem can't be done, and that's not one of my multiple choice options. So therefore I got to assume something. The other thing is, because it does say that this is burned in the presence of oxygen, we breathe oxygen all the time as mammals. And so therefore we just assume that we are burning something in a place where there's plenty of oxygen around. We're not suffocating. And therefore there's also enough oxygen for this reaction to burn just fine. So those are my assumptions. So I do have my actual. So I have my 40.5 grams times 100%. I just need the theoretical. That's the only thing I need. And you know what? We can calculate that. So since I have 25 grams, so that's what we're going to do. We're just going to calculate that. 25 grams of sulfur dioxide. Did they give me the molar mass? It would be so nice. Oh, they did, right there. Don't scribble over it. Now I can't read it. 76.15 grams sulfur dioxide in 1 mole of sulfur dioxide. I did grab sulfur dioxide, right? Good. And then I want to deal with going from my moles of sulfur, of carbon, sorry, whatever this is supposed to be, carbon disulfide. But I don't want carbon disulfide. I want my product, sulfur dioxide. So I'm going to go from here to here. So I've got 1 to 2. So 1 mole of carbon disulfide in 2 moles of sulfur dioxide. And then because in percent yield, I'm already in grams here. That means that I need this to also be in grams. I need those units to match each other. They could both be in moles. So they can both be in different units, but they have to be the same. So those units cancel out. So I'm left with percentage. So now I just need to go to grams of sulfur dioxide, which is right here, 64.07. So in 1 mole of sulfur dioxide, I already forgot the number, so 64.07 grams. So there's all my math. So I'm going to take my 25 that we started with, divide it by the molar mass of carbon disulfide, multiply it by the stoichiometric ratio, which is 2. Technically, I'm also dividing it by the stoichiometric ratio, which is 1, and then multiplying it by the molar mass. After all that's said and done, I get 42.63 grams. So that's what then goes over there. 42.63, 40.5 divided by 42.63 times 100 is 95.0035%. I'm off a little bit. That happens. So I can certainly go back and redo all of my math, but honestly, sometimes this happens to us where we did an okay job and something weird has happened, but there's one answer that's super closer than everything else and we just roll with it. Yeah, I'm gonna get frustrated and I'll probably go back and redo this one after the video, but I don't know if you guys can tell, but my voice is starting to go. And I still have 7 more problems to do, so I'm actually just gonna keep going. So if you don't like the fact that I didn't get exactly the right answer, but I'm moving on, you can come see me in office hours. You can go to the Peer Tutoring Center. You can go to the chemistry clinic. I am going to say that I probably just, I'm going to type this in my calculator one more time to see if I messed up. 76 times 2 times 64.01. That's 42. Oh, I did. There's supposed to be a 0 in there. I was close. It's 42.063. I missed a digit when I was typing in my calculator. So now that I have 42.063 on the bottom, let's see what happens. Now I get 96.28. Am I closer? There we go. I'm still a little off, but it's closer. Being wrong in the last digit, I am not worried about. Okay, so I wrote one number and that got me off a little bit, but I fixed it. So now we're better off. One other thing to point out about this question is if you'll notice, there are a lot more molar masses in this problem than we actually used. So it gave me the molar mass for both of the reactants. It also gave me the molar mass for both of the products. And I did not need all of that. We do this for 2 reasons. One, we live in the information age. So looking up the molar masses for things is super easy. So if this was a real world problem, you would be able to get all of these molar masses and it's your job to figure out which ones you need and which ones you don't need. So that's one reason. The other reason is we often use the same problems, but just swap the reactants and the products on different versions. So odds are really good that version B of this problem just asked for like the amount of carbon dioxide, or gave the amount of oxygen and assumed there was an excess of carbon disulfide. It'd be a little weird, but that happens to us a lot where we just kind of swap things around. So we tend to just put all the molar masses in the problem. So if we want them, we have them. That's that one. All right. 2, 3. Okay, here's a ranking one. So rank by increasing the boiling point. So that means that I'm going to go from lowest to highest, which means I need to go from weakest intermolecular force to strongest intermolecular force, and that's the goal. So honestly, so if this was, do I have just a box thing I can put over this? Insert a box. Will you give me a box? That's a circle. A box. A box. That's, fill in the box, please. I don't know how to fill in the box. I'm sad now. That's too bad. Anyway, what I wanted to do is I wanted to cover up my answer choices because I don't care about the answer choices right now. I very much just want to think about this and not think about what is in front of me. I just want to ignore all of these, which is apparently impossible right now because I'm on a computer and I don't have a piece of paper. And I don't know if you guys can tell, but I'm a little tired. Anyway, that's fine. I could also crop this. I'm just going to ignore them. So I'm not looking at A through E right now. All I'm going to do is to think about these guys and what I have. So I got lots of carbons. So I got 2 carbons and some hydrogens. So this is non-polar. I've got, that's not carbon. What is that? CS. CS. Where is CS? It's down here. Hey, that's a metal. That means that's bromine. That's ionic. I got a metal and a non-metal. Look at that. That's ionic. This thing's got carbons and hydrogens, but it also has oxygen to a hydrogen. So this has, not only does it have dipole, but it also has hydrogen bonding, which means it also has dispersion forces. And this also is nonpolar. Nothing but carbons and hydrogens. So in this case, so ionic is actually one of the easiest ones to rank. So we can have a big discussion about whether ionic counts as an intermolecular force or not. But regardless, for boiling point, it's going to be the highest boiling point. It's an ionic thing. It's going to have the highest boiling point. Those are whole charges. Whole charges, highest boiling point. Next up is going to be my hydrogen bonding. Whatever has hydrogen bonding is going to come next. So that's next up. Then I have my 2 nonpolar things. So since both of these are nonpolar, I need a way to figure out which one's stronger than the other. One of these has 4 carbons and one of these has 2 carbons. The one with 4 carbons is going to have more dispersion forces. So we talked when we did instantaneous dipole, we mentioned the fact that this is just a random thing that occurs. The more atoms you have, the more carbons you have, the statistically more likely you are to wind up with more dispersion forces because you just have more atoms. So this then is going to be more likely to be here. So it's going to be greater dispersion forces, and this should be the lowest one. So that's my ranking. And now I need to find the answer choice that fits my ranking. So I need to start with C2H6. Only three of them do that, but these 2 don't. Then I need the one that has the ionic one on the right. Only 2 of them do that. So I want this to be here, and I want this to be here. And then I need my nonpolar things to be together. That's this one. So definitely recommend you cover up all the answer choices when there's ranking stuff. It's going to make your life a lot easier if you can. All right, there's that one. Next up. Sucrose reacts with potassium chlorate according to the following balanced reaction. And hey, they balanced it for us. We've had this conversation before, but I'll say it again. We're just going to trust all those numbers. Suppose a certain number of grams of our sucrose is mixed with a certain amount of potassium chlorate. What mass of carbon dioxide will be formed in the reaction? So this one, because it has one of our reactants and it then also gives us the other reactant, this is a limiting reactant problem. It doesn't say that, right? It doesn't ask you for the limiting reactant, but this is in fact a limiting reactant problem because you have numbers, you have values for both reactants. So since you have values and numbers for both reactants, this is a limiting reactant problem. So the goal then is to go to mass of carbon dioxide. So I'm going to do limiting reactant the way I like to do limiting reactant. If you don't like it this way, have I mentioned the Peer Tutoring Center? Have I mentioned the Chemistry Clinic? They're fabulous. And they will probably do it a different way. Because there are at least 3 good ways to do limiting reactant. I'm just going to do my way, which is dealing in reactions. So everything's grams, isn't it? Yep, everything's grams. Yippee! So I'm going to do one in red for my sucrose. So what we're going to do is we're going to look at both of the reactants. So we are going to do a similar calculation 2 times over. So here is my grams of C12H22O11. And the first thing I'm going to do is get this into moles because we're going to need to use the balanced chemical equation. Anytime we need to use the balanced chemical equation, I'm going to need moles. Unless I do already have my molar mass was given to me in the problem. So I don't have to calculate that. They gave that to me. So molar mass is hanging out right there. So I'm just going to use that number in 1 mole. I'm actually going to write the word sucrose. It's a little easier than C12H22O11. Then I'm going to use my coefficients. I want carbon dioxide. So there's a little invisible 1 right here to go to my 12. So in 1 mole off of the balanced chemical equation of sucrose, there are 12 moles of carbon dioxide. Then, oh, I wasn't going to do it that way. That's one of the ways I wasn't going to do it that way, though. I was actually just going to go not to 12. I was just going to say, I was going to use reactions. That's what I do. So this whole thing is one reaction. So the nice thing is if once we go from grams to moles, I'm just going to say that in 1 mole of sucrose, I have 1 reaction. This is going to let me identify the limiting reactant relatively quickly because all I'm actually doing is dividing by the stoichiometric coefficient. So grams to moles. Don't forget the 300. I haven't had breakfast yet. Sorry, I'm like, why is my brain not braining as well as I'd like it to? Oh, I haven't eaten breakfast yet. That's okay. I'll do it soon. So if there's enough, if I could actually use all of my sucrose, I could do this many of my recipes, this many of my reactions. Let's see if I actually have enough to do that. So there's 1. Then my other one is to deal with the potassium chlorate. So this is 954. The odds that I wrote this question are very low because I don't usually do triple digits. Biochemists, everything goes in test tubes. That's a lot of potassium chlorate. molar mass 122.55. Maybe it was me. I don't remember. I started using Excel for some of my my calculations when I figure out exams. In 1 mole of KClO3, and then we are going to use the reactions. So what's my stoichiometric coefficient? It's an 8. So there's 8 moles of KClO3 in one reaction, in one of the whole thing. So if I was going to do this whole thing as reactions or recipes, how many times could I do this whole thing if I have enough of that KCl? And I wind up with 0.9734 reactions. This is technically moles of reactions, just in case you're curious. We are technically still in moles, but reactions. The smaller number is the right one. So this is, again, one of those times where if I had pieces of bread and pieces of cheese and I'm making sandwiches and I have 2 pieces of bread and I have like 30 pieces of cheese, 30 pieces of cheese sounds delicious, but I can't make that many sandwiches because I only have 2 pieces of bread. So my smaller number is going to control what I can actually do. So that then tells me what my limiting reactant is. Problem didn't actually ask for that, but I found it. I needed to find it. What mass of carbon dioxide will be formed? So the beautiful thing is I already have this reaction. So I'm actually going to use that number. We calculated it. It's real. So I'm just going to say that because I can make, I'm going to get rid of my circle, because I can make that many reactions in one reaction, I have 12 moles of carbon dioxide. And because I have made 12 moles of carbon dioxide for every one reaction, there's my molar mass, 44.01. In 1 mole of carbon dioxide, I have 44.01 grams of carbon dioxide. So times 12 times 44.01 gives me 514.06 grams CO2. 514, yay, right there. So limiting reactant is long because you have to do that same calculation. You have to assess both reactants. Going to reactions is my personal favorite. I think it saves a little bit of time in a lot of cases because most other techniques make you go to a different part of the reaction. So it makes you either solve for another reactant or makes you solve for a product. So this basically just stops a little bit earlier. So personally, I think it's faster as long as you then use the reaction number to continue your calculation. But you do you. There's, like I mentioned, at least 2 other good ways to do it. No, I will not do all 3 of them right now because how long is my follow-up video so far? 50 minutes so far, and I'm not done yet. If you are interested in the other methods, again, I'm pretty confident that the Peer Tutoring Center or the chemistry clinic or me, actually, I think I'm the only one that does reactions. So I'm pretty sure that the other instructors will also get you something different. All right, number 11, what will not be experienced by a mole of the molecule below? So it says a mole because we are trying to talk about intermolecular forces. And all of these down here, except really for ionic interactions, again, do those count as intermolecular forces or not? But one thing to note on here is since they're intermolecular forces, there are atoms. Those are going to have electron clouds, so it should have dispersion forces. Those should definitely be there. I've got lovely, beautiful oxygens with lone pairs. They are there, even though they're not drawn in there. They are assumed to be there. So I'm absolutely going to have dipole-dipole interactions. That'll be there. And I have nitrogens and hydrogens together. So I absolutely have hydrogen bonding, which means I can have hydrogen bonding and dipole-dipole interactions because those are both hanging out in the molecule, but in different places in the molecule. Also, technically, you could argue that hydrogen bonding to itself is a dipole-dipole interaction. Anyway, those are also there. But what's not there, there's no whole charges. There's no whole charges, so I don't have any ionic interactions, which makes this the correct answer. So there we go, number 11. Next up, 15. So they gave me stoichiometric coefficients. I'm kind of excited about that. I'm going to trust those. I don't have to balance this equation. Great. Determine the theoretical yields of potassium phosphate. It's got a molar mass if you start with 49 grams of KOH. Really wish it said in excess of H3PO4 of that, but it didn't. So we are just going to assume that there's an excess because, again, if I don't make that assumption, I can't go anywhere, and I've got a bunch of multiple choice options, so I've got to go somewhere. So also, this is the one time where actually I do need my answer choices to tell me what unit I need. These are all in grams, so therefore we're going to go to grams. Sometimes they're all in moles. But I actually did need that information off of my multiple choice questions because it didn't actually tell me if I was in moles or grams in the end. Theoretical yield just means do the calculation, essentially. So because technically anytime we're doing the calculation, we are doing theoretical yield because the calculation is theoretical. Actual would be what happens in real life. We're all in paper and pencil. It's not real life. Okay, so 49.0 grams of KOH, which is this reactant. Lovely. That's in grams. So whatever goes on the top here has to be down here. So this needs to be grams of KOH. This is 56.018 grams in 1 mole of KOH. Then from here, I don't want KOH, I want potassium phosphate. So I'm going to say that for my chemical reaction, 3 moles of potassium hydroxide, I actually get 1 mole of potassium phosphate. And since I in fact get that ratio from my balanced chemical reaction, I can then continue on to grams. So then I can say, again, whatever's on the top here goes on the bottom here. So my mole of potassium phosphate, I've got 1 of those in the molar mass, 212.27 grams. So do notice that I keep using these railroad tracks, but I keep doing the same thing over and over and over again. I'm going to start with the number that they gave me in the problem. I'm going to head towards the thing that they asked me to find. As I do that, one of the things that's unique about this exam is basically these are not the same thing. I know they both have potassium in them, but that's going to make me use my balanced chemical reaction. Anytime I have to use my balanced chemical reaction, I'm going to have to go to moles because that balanced chemical reaction is always in moles. So that's one of the things that we keep doing over and over again is heading to moles. The number I get out of my calculator is 61.8922. That's way too many digits, but that's fine. Great, 61.9. So not 61.9. Excellent. Okay. Boron trifluoride reacts with hydrogen according to the following balanced equation. Suppose 2.0 0.35 moles of boron trifluoride are mixed with 1.45 moles of hydrogen, how many moles of HF would be formed? So what we have here is we have two sets of numbers, this one for boron trifluoride, and then I have another number for hydrogen. Those are both reactants. And I would like moles of HF. So I would like a product. So because I have numbers for both of my reactants, this is a limiting reactant problem. So it's a limiting reactant problem because I have numbers for both of my reactants. So the nice thing is everything's in moles. So I am also still going to use that reaction. So I am just going to use this whole thing is one reaction. Sorry, I'm going to use my shorthand a little bit. So in 2.35 moles of boron trifluoride, I have 2 moles of boron trifluoride in one reaction. Please note that if I was doing this on my calculator, all I would be doing is dividing, take 2.35 and divide it by 2. And that's the only thing I have to do here. For hydrogen, it's 1.45 moles hydrogen. And then from my balanced chemical reaction, I've got 3 moles of hydrogen in one reaction. So I just take 1.45 and divide it by 3. That's 0.483. Sorry, these are both supposed to be in reactions. So that's how many times I could do the entire reaction. Whichever is the smaller number is the one we need to use. My goal is to get 2 moles of HF. So I'm just going to take my smaller number and run with it because I could make 0.48 reactions. I can make a grand total of 6 moles. So in one reaction, I can make 6 moles of HF. So take that number and multiply it by 6. When I do that, I get 2.9, like right on the nose. 2.9. Notice in here that we did provide a bunch of molar masses. We provide a bunch of molar masses to try to throw you off. We never needed grams. Never needed grams. We gave them to you, but we never actually needed grams. So the only thing we needed to do is figure out which one was a limiting reactant, which we could do just dividing moles by the stoichiometric coefficient. Whatever number is smaller is the right answer. And again, I'm using whatever number I get. So I'm actually using that reaction number to continue my calculation. I don't have to start over because I figured out how many times we could do the whole reaction. So I just treat that reaction as one big thing, like it's a new unit, like it's one recipe, right? So like when you make a cake, even though there's a whole bunch of pieces of the cake, that is one recipe, one whole thing. Oh, I don't know where I am. Do I really have 2 left? 2 left. Then I get to eat breakfast. Oh, I apparently saved the short answer for last. Ammonia reacts with oxygen according to the following equation. If 0.398 moles of ammonia react, how many moles of hydrogen would be formed? So again, there's no information about oxygen in here. So we are just going to assume that we have as much oxygen as we need and more. The key actually has how we do this problem, but I will write it out since people asked about it. So you start off with the given, which is the moles of ammonia. And then the goal is to go to moles of water. That's over here. Since I need to go from ammonia to water, and those are not the same thing, I'm going to use the stoichiometric coefficients in my balanced chemical reaction. So starting with 0.398 moles of ammonia, and then in my balanced chemical reaction, I have 4 moles of ammonia for every 6 moles of water. And that's all I needed to do. It didn't actually ask me for grams at all. So that's it. That's all. So 0.398 divided by 4 times 6 is 0.597 moles ammonia. This says 3 digits, 1, 2, 3, 3 digits. That's it. So this one looks more complicated than it is. So just whenever you're looking at these math problems, I really would recommend like underlining or highlighting or doing something to look at like what is your given and where are you going? What do you actually need? Because there's lots of things we ignored in this setup. So that might be why y'all are having so many questions about this. Is part of this is to figure out what pieces you actually need. So that's why I've been trying to highlight, underline, scribble somehow on the problem, is to give that information of what I'm paying attention to, but it also tells me what I'm not paying attention to, what I'm going to ignore as we go through. All right. Last but not least. Following molecule, firefly, D-luciferin, is a substrate of the enzyme luciferase, is involved in the bioluminescence observed for fireflies and sometimes of beetles. Some types of beetles, not times of beetles. So I need sigma and pi bonds. I need hybridization for things that are labeled, and I need ideal bond angles. Cool. So sigma and pi, I'm going to do pi bonds first. I am looking for double and triple bonds. 1, 2, 3, 4, 5, 6. There's no triple bonds, there's only double bonds, so therefore there's just 6 pi bonds, 1 pi bond for every double bond. If I had triple bonds, there would be 2 pi bonds for every triple bond, but there aren't any triple bonds, so it's just pi's, so that's all I got to worry about. Sigma bonds. I'm mentally laughing just a little bit because yesterday I was being honest when I said that I hadn't looked at the exam questions yet, but that's not true this morning. And one of my jobs was to double check all the sigma bonds for all the versions. So I have written out a lot of molecules this morning and done a lot of really careful counting. Let's see if I can do it again. So when we're looking at this, one of the things to keep in mind is there are hidden hydrogens. So everywhere where there is a bend, right here, this is actually a carbon. This carbon has 1, 2, 3, 4 bonds, no extra hydrogens. This carbon here has 1, 2, 3 bonds, which means there actually is an extra hydrogen here. This carbon here has 1, 2, 3, needs an extra hydrogen. So when I'm counting that, keep in mind that that carbon looks like this, where it has a double bond here and a single bond here, but does not have a complete octet. So I am adding a hydrogen on to complete the octet. This carbon has a double bond and 2 single bonds. That's a complete octet. This nitrogen just gets a lone pair. This carbon has a double bond and 2 single bonds. That's a complete octet. This sulfur just gets lone pairs because it acts like oxygen, which also just gets lone pairs. Oxygen would get 2 lone pairs. Sulfur gets the same treatment. This carbon here has a double bond and 2 singles. That's a complete octet. This carbon has a double bond and 1 single bond. It needs a hydrogen. This carbon has a double bond and 2 single bonds. It's fine as it is. That's a complete octet. The sulfur gets 2 lone pairs. This carbon has 2 single bonds. It therefore needs 2 more. This carbon has 3 single bonds, so it needs 1 more. That's a hydrogen. This nitrogen gets a lone pair. This carbon has a double bond and 2 single bonds. It's fine as it is. This oxygen actually has 2 lone pairs. This oxygen also has 2 lone pairs. There's a hydrogen. So now that I've edited my molecule, I can count my sigma bonds. Hopefully. Here we go. There's a sigma bond in between the hydrogen and the oxygen. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. in between the oxygen and the hydrogen. So yes, I just slashed all over this. Good news, it's a video. So y'all are welcome to pause me and rewind me to go back, but I did actually get to 28. And that's the right answer. So usually in here, the tricky ones were either the hydrogens I had to put in blue, and then the fact that there's a single bond in between my oxygens and my hydrogens. Those are the ones that sometimes hide from people because it seems like everything is there for you, and it is, but there's also a single bond that's not drawn. It's assumed that it's there. Okay, hybridization by atoms labeled 1 and 3. So what I am going to do is I'm just going to redraw those. So the one that's 1 is a carbon with a double bond going down and a single bond. That's not a complete octet, which means there's a hydrogen off of it. And if we come back over here, we already decided that. So here it is, but this now has 1, 2, 3 electron domains. 3 electron domains is sp2 hybridized. So that's what that is. And then somewhere else, 3, I want 3 is this nitrogen. So my nitrogen has a double bond, a single bond, and a lone pair. We do assume that nitrogen has 1 lone pair. So this is 1, 2, 3, also sp2 hybridized. Ideal bond angles for atoms number 3, which we've already drawn. Ideal means I don't care about greater than or less than. So I just care about this bond angle in here because it's sp2 hybridized, or it has 3 electron domains. That's trigonal planar, so that's 120 degrees. And the last one is atom number 4. Where's atom number 4? Oh, right there. So that is a carbon with drawn 3 single bonds. That's not enough, which means it does have a 4th. So this is tetrahedral. Since it's tetrahedral with 4 electron domains, it should be 109.5. All done. That's the last of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Last night when I counted, there were 9 questions to do. I've done 9 questions. I'm just going to cross my fingers with the right ones. So hopefully this helps y'all out with exam preparation. Again, highly recommend Peer Tutoring Center and the Chemistry Clinic this week. There's lots of drop-in hours to talk to people and find them. So good luck.